Hi everybody, coming into the home stretch here. So we don't do small questions in astronomy, so we're going to talk about the history of the universe from the very moment of creation until its death, and we're going to cover it in a single lecture. Now, we're just going to give you kind of the broadest overview of what we think happened during the Big Bang and what are the possible end states for the universe, how it might die. And then we're going to figure out exactly how our universe, our actual universe, is going to die. So strap in and let's get started. All right, so cosmology is literally the study of the universe, how it was born, how it evolves, and how it dies. So that brings us to the final subject that we'll be talking about for this semester, and how was the universe created and how will it die? So you'll need tool 29, looks like this. Make sure that you've got that out. You'll notice that there's not any real work that needs to be done on this particular one. That's because it truly is class notes. It's kind of summarizing everything in one place. You'll be using the practice to organize most of your learning. All right, so we talked about the idea of the expansion of the universe. If the universe is getting bigger, then if I run it backwards in time, it must have been getting smaller. Well, you guys know from star formation and from stellar evolution, as I squeeze something, it gets a lot hotter and a lot more dense. So by the time I got back to the Big Bang, the actual instant of creation, this universe must have been incredibly hot and incredibly dense. So before we can get started, there's a couple of things we need to talk about. You've probably heard of E equals mc squared. Energy is equals the mass times the speed of light squared. What this means, this is Einstein's famous equation, but what this means is that mass and energy are two forms of the same thing. They can be converted back and forth into each other. So you can have matter, you can put it in with antimatter and convert it all into energy. Or maybe you do nuclear fusion and convert just a tiny fraction of it into energy. But it works the other way too. If I have energy, two highly energetic particles can come together to photons and they can create matter from that. So it goes back and forth. So remember, you matter. Unless you multiply yourself by the speed of light squared, in which case you energy. All right, so in the early universe, the total energy of the universe consisted of both radiation and matter. Initially, it was almost all radiation, and then we'd get a little bit of matter that would last for a very short period of time before being annihilated. Then at this crossover point here, as the universe cooled, matter started to dominate. And when matter started to dominate, then space suddenly became black, basically, and you could see in between all of the stars that were there. We also need to talk about this idea of particle creation. Now, this is not a quantum mechanics class. We're not going to get into the quantum mechanics with this, but this is basically what we were talking about. I can have two gamma rays that can collide together, and their energy can actually be converted into mass, and we'll always get an electron and an anti-electron, so antimatter out of this. Same thing, if I have an anti-electron and electron and they come together, well, most of you know that if I have matter and antimatter together, they annihilate each other. Well, they convert into gamma rays. So the early universe then was full of these particles and radiation because they'd be created and destroyed, created and destroyed, created and destroyed, and created and destroyed because the mass was so high, we were getting lots of these collisions. So let's look at some of the changes in time. We had this instant of the Big Bang, and then suddenly the universe got extremely big, much faster than the speed of light, and that's called the inflationary period. After that, it started to expand quite a bit more slowly. But what we're seeing here, this is when the universe was all matter, was all radiation. We can't see anything beyond that point, but we can see that radiation because it's expanded out and cooled and fills the universe now. We'll be looking at that in a second. All right, I want you to break the history of the universe into two phases. The first 20 minutes, and I mean literally the first 20 minutes, the first 20 minutes that ever happened. So there will be some events that occurred there, and then everything after that first 20 minutes. So after the instant of the Big Bang, up until about 10 to the minus 43 seconds, we call this the Planck era, but basically the temperature was a 1 with 32 zeros after it, and the density was 1 with almost 100 zeros after it. Incredibly hot, incredibly dense. The universe is just these radiation and subatomic particles being created and destroyed, and created and destroyed, and created and destroyed. Prior to 10 to the minus 43 seconds, quantum mechanics dominates, and so I really can't say what happened before then. So we're going to pick apart our lesson right here with 10 to the minus 43. Well, by the time the universe was 10 to the minus 10 seconds old, It had cooled just a little bit, 10 to the 75th, but at this point, the universe mysteriously expanded by a factor of 10 to the 50 in 10 to the minus 32 seconds. Well, that is a lot faster than the speed of light. Well, you guys know from the black hole lecture, the only way that I can have something traveling faster than the speed of light, I need this negative matter that, causes things to be pushed away. So this is called the inflationary period, because the universe literally blew up like a balloon. So if that negative matter existed, that's what would have been powering this. We can't think of anything else that could be pushing this. All of this is the blink of an eye, less than a blink of an eye. This is 1 times 10 to the negative 10, so 0.9 zeros and a 1 seconds. After 3 minutes, after the universe was created, it had cooled down enough that I could get hydrogen and helium nuclei, really, but they were under such pressure that the universe itself was fusing hydrogen into helium. This was not in stars. This was just the universe was so dense that the universe was kind of like one big giant star. Also during this time, the protons and antipart protons started annihilating each other. We should have had exactly as many protons or normal matter as we do antimatter. And so when they annihilate each other, there should just be nothing left. There should just be energy. For some reason, there was just a little bit more matter than antimatter. Not much, just a tiny, tiny, tiny bit more. Everything else annihilated, and all that was left then was the matter from that. So this is why our universe seems to be made up almost entirely of matter. We can make antimatter, and antimatter is certainly made in fusion processes and things like that, but the vast majority of the universe seems to be matter. After 20 minutes, that process ceased, and the universe was left with 75% hydrogen and 25% helium, which is about what we see today. So even before the very first stars were born, there was some helium left in the universe because it was created when the universe itself was fusing that hydrogen into helium. So after 20 minutes, we really only have two major events. After 380,000 years, the temperature dropped to 3,000 Kelvin. Now remember, this is a billion Kelvin after 20 minutes. That's the entire universe, not just certain parts of it. That's the whole universe itself. Well, it had cooled to 3,000 Kelvin. So it's cool enough for full atoms to form. At that point, matter now dominates. And so this is as far back as we can actually look with our telescopes. And this is called the cosmic microwave background. I'll be talking about that a little bit more in a minute. Then after a billion years, anywhere from 100 million to a billion years, we get the first stars and quasars begin to shine. So the earliest galaxies and the earliest stars were formed after 100 million to a billion years after that. Temperature had dropped 10 to about 100 degrees Kelvin. And today, of course, it's continued to expand, and so now the average temperature is much, much colder. It's about 3 degrees Kelvin. So the universe has cooled from these 10 to the 95 degrees Kelvin all the way down to basically 3 degrees Kelvin, just 3 degrees above absolute zero. So in 1965, Penzias and Wilson, these were two astronomers, had built this radio telescope that you see behind them there. And so they were measuring the amount of microwave background, and they kept getting a signal no matter where they looked. And they realized that it was coming from all parts of the universe at the same time. So they mapped that out, and they got a perfectly matched prediction of the universe glowing at a temperature of 2.73 degrees Kelvin, which exactly matches the prediction of what it should look like if we had 14.5 billion years of Big Bang, where it had expanded out and cooled down from that point. So this is in the microwave. So right after the Big Bang, the energy of the universe was in gamma rays, but as it expanded, it cooled. Well, you guys know from Wien's law, as it cools, it becomes more and more redder. So I went from gamma rays down to optical, then infrared, and today it's in the radio, actually the microwave from there. There's still some mysteries left. So in the universe, the initial universe should have been basically perfectly smooth. There's no reason why there would be any clumps or anything like that, which would mean we shouldn't have stars or galaxies. The structure that we see in the universe, these big clumps and voids of galaxies and stars in between and things like that, had to have come from somewhere. But the initial universe, if it was perfectly smooth, would just form one big giant star. Why is the overall distribution of matter so uniform? No matter which direction I look, I'm going to find galaxies. So it's not like all the galaxies are here and then there's nothing over here. Second thing is that the density of the universe is very close to the critical density. And what I mean by that, we're going to get into that when we talk about the death of the universe, but that's the balance point between will the universe expand forever or will the universe finally stop and then come back and collapse? We are very close to that critical point. So inflation, that idea that the universe expanded by a factor of 10 to 50, actually can explain the structure that we see. So there's always these particles and nanoparticles being created all the time. It's happening right here where I'm pointing, right here in space. 10 to the minus 43 meters, so much smaller than you could possibly measure. It's literally impossible to measure, but it's being created all the time. We call that the quantum foam. Well, that's on a tiny, tiny little scale, but that happened in the early universe. There was still this quantum foam, but then it got magnified by a factor of 10 to the 50. And so you see what starts out as foam here now becomes very large scale. And so where I have these dark areas here, that's where I've got more density. And so the galaxies actually formed in these bubbles. And if we look at the large scale structure of the universe, we see that all of the galaxies are forming on the surface of these bubbles, these clumps, forming clumps with voids in between. That's just a magnification of the quantum foam. So the Wilkinson microwave and anisotropy probe, WMAP, that's what everybody calls it, is mapping out these tiny, tiny variations in that cosmic microwave background. And we see that it's not perfectly smooth the way our Penzias and Wilson thought. In fact, there are tiny variations that are due to that quantum foam being magnified to the size of the universe from there. So these are basically the seeds for what would become the galaxies. Remember, when you're looking at this, you're looking at 380,000 years after the birth of the universe. So you're looking back in time. So wherever you see the dark areas, that will eventually become a galaxy. Inflation also explains why we're close to the critical density. So think about a balloon. As that universe expands, it's still curved, but to the point of view of an ant, when it was small, it was really curved. But as it got bigger, the ant doesn't see that curve. It's just like when you look outside your window. The Earth is curved, but you don't see that. You don't perceive it because you're an ant compared to the size of the Earth. Well, now consider the size of the universe. If I have this flat universe, then I'm going to be very close to that balance point between expanding forever and collapsing back down to the big crunch. It also explains why the temperatures at 2.73 degrees Kelvin that I see is the same everywhere in the sky. So even when I look over here and when I look over here, it's still the same temperature. Well, you may say, well, wait a minute, how can that be? Because if anything changes here to try to cause that to be the same temperature, it would have to propagate faster than the speed of light. And that's actually what happened. These two parts of the universe used to be very, very close together. Well, if they're right next to each other, then sure, they can influence each other's temperature so that they settle out to be basically the same temperature. And then when the inflationary period happened, those two pieces got pushed very far away from each other. So now different parts of the sky still have the same temperature. So there's a lot of evidence for this inflationary period, and that inflationary period kind of depends upon having that faster than light expansion. So our dilithium crystals are out there. We just got to find them. All right, so we've talked about the birth of the universe. So now let's look at how the universe is going to die. There are three possible ways that the universe could die. It could expand forever, but reaches zero after an infinite amount of time. So it's always slowing down, but never quite getting to zero. It could just keep expanding forever and not even get close to zero. So it just never slows down. No, slows down to zero anyway. Or it could slow down to zero and then turn around and come back and collapse. So if we assume that the only force that acts over these large distances is gravity, and we're going to see in another lecture that may not be the case, but then how the universe is going to die depends upon its density, how much mass it's got, and how compact that mass is. Think about it. Mass is what's producing gravity. So if I've got this initial explosion, boom. If I've got enough mass, if this part of the universe is pulling on this part hard enough, it will slow down and then it will come back and collapse back down. Just like when you take your pen, you throw it up, the Earth has enough mass to slow it down and bring it right back in. On the other hand, if I take that pen and I'm throwing it really, really fast, or if the Earth is really, really tiny and there's not enough gravity for it, then it might expand on forever. Okay, so those are the, and then this first one here is kind of the knife edge in between. That's that critical density. So let's assume that the actual density of the universe is omega, because, you know, alpha and omega, beginning and end. So we're talking about the end of the universe here. And the critical density, the density that determines whether it expands forever or whether it comes back to the big crunch, we're going to call that omega 0. We can then write our three cases like this. If the actual density is less than the critical density, then there's not enough mass to stop the expansion of the universe. The universe will expand forever. If they're exactly equal, then it will stop, but only after an infinite amount of time. That's that border, that knife edge case. If the density, the actual density, is greater than the critical density, then it'll reach a stopping place and everything will come back down to the big crunch. Now, I gotta say, I find the big crunch to be extremely philosophically satisfying, because you don't have to answer the question of what was going on before the Big Bang. The universe has just always been here. It exploded, it expanded out, it stopped, it came back, it crunched, it exploded, it stopped, it came out, and crunched. And so the universe has literally already existed. You don't have to explain, you know, what happened before the universe was born. So I like this one a lot philosophically. We'll have to see if it actually matches the data. So the critical density, that omega 0, is actually a very small number, 9 times 10 to the minus 27 kilograms per cubic meter. That's about 5 hydrogen atoms in each cubic meter. A meter, remember, is a little more than 3 feet. So imagine having just 5 atoms in that area. Space is very, very, very empty. Now, the matter that you're standing on, the Earth, and the air that you're breathing is a lot more than 5 atoms per cubic meter. But we're a tiny, tiny speck compared to the rest of the universe. Most of the universe is so empty, it balances out these dense places like us, like where we're living. So if the critical density is 9 times 10 to the minus 27, we can look out there and we can count all the stars and all the things that are glowing out there. And we only get it to be about 3% of the critical density. So it's not even close to enough to stop the expansion. However, there is this dark matter, which may or may not be actual dark matter, but it might be our physics that's wrong. But as long as it has that effect of pulling on everything, it works the same. If we include that, we get to about 30% of the critical density. So the end result then is that we are nowhere close to having enough matter in the universe to close it. The universe is going to keep expanding forever. So our universe will die a cold, lonely death with no one to mourn its passing. And that's where we're going to stop. So make sure that you've got your cosmology practice sheet here. This is serving as an organizer for you to kind of figure out what's happening with star birth, which is the first part, and universe birth and universe death at the bottom. So that's it. Now you know how the universe was born. Now you know how the universe is going to die. Not the way I wanted it to work out, but the science is what the science is, and so we just have to go along with that. The universe is going to expand forever until one by one the stars go out. All of the gas and dust that could be used to make new stars will be used up. The universe will slowly blink out, and then they will continue to expand out until it's a cold and lonely death. We'll see you next time.